Hello students, let's continue our discussion on modulation. Modulation, as we know, is varying one of the parameters of the carrier wave linearly with respect to the message signal or baseband signal. In case of, let us define amplitude modulation. Or AM. AM can be as varying the amplitude of the carrier wave CT linearly with the message signal MT. In case of amplitude modulation, the amplitude parameter of the carrier wave is being varied with respect to the message signal. So let's say S of t be our modulated wave. And let us write it mathematically as where CD is the carrier wave and MT is the message or baseband signal. Carrier wave with frequency fc. So you can see here the amplitude of the carrier wave is being varied with respect to the message signal. Hence this is called amplitude modulation. The quantity Ka is called voltage sensitivity. And its SI unit is inverse of the voltage. So to make this product dimensionless, And Ka is a property of the modulated system. The modulated system that we are using. Let us do the graphical representation of ST, that is the modulated wave. Let's say this is the graphical representation of a low frequency message signal. Now, the message of the modulated wave is given as 1 plus. Now, what we need to do, we have to shift MT by unit 1 and scaling by a factor of K. So we will do a performance shifting and scaling operation here. So it will be somehow like this is so this is our signal 1 plus Ka into MT. Now the value of Ka, the absolute value of the product Ka multiplied by the message signal is always taken less than 1, so as to keep this signal always positive. To keep this signal always positive. let's say CT is the carrier frequency or the carrier wave. And so on, and whose amplitude is plus A C to minus AC. Now looking at this equation, what we have to do? We have to multiply these two signals to obtain ST. Keep this in mind, we are choosing the frequency Fc in such a way that Fc is much larger than the maximum frequency of the message signal. Let Fm be the maximum frequency of the message signal. Let us multiply these two signals to obtain ST. Finally, so if this is our message signal MT, we are doing the multiplication. This is our message signal. So this will be representation of the modulated wave ST given as given that the absolute value of this, the multiple Ka times of MT, is always less than 1. So this is the graphical representation of the modulated wave. We can observe here one thing, is that the carrier wave is varying with a frequency of the same as the carrier frequency. This time period is same as that of the carrier frequency, but the amplitude is varying with the message signal, or you can say empty forms the envelope upon CT, the carrier wave. As you can see, the amplitude is varying with respect to the message signal. Hence, this is called amplitude modulation, and the corresponding wave is the modulated wave, amplitude modulated wave. We can write here as amplitude modulated wave. Given the condition that the absolute value of the multiple k times of the message signal must be less than 1. Suppose if we select the modulus value of this quantity as greater than 1, then what will happen? There will be chances that the signal that it will have a negative value. Then what will happen? Suppose in that case, if we are taking this product as greater than 1, then what will happen? Suppose this is the envelope of the this is the envelope of the message signal. Now in that case, the ST that we will obtain will have a phase reversal at zero crossing, and you can see here a 2:1 relationship is obtained, and there is phase reversal. You can observe here there is phase reversal in the case when we take the product k times of empty less than greater than 1. And this term is called modulation. And suppose we multiply this term with 100, then this will be called percentage modulation. As you can see, there is distortion in the envelope of the modulated signal. Then in this case there is envelope distortion. And we call this as a case of overmodulation. So we can write a note point here. In order to avoid overmodulation, the product or the absolute value of k times of empty must be less than equal to 1, where equal to 1 will be the critical condition. This is a case of critical modulation. Now let us do the spectral representation of the modulated wave ST. That means representing the modulated wave on the frequency domain. Now ST is given as AC times of 1 plus Ka mt into cos 2 pi fc into t. Again writing now, in order to represent the signal ST in frequency domain, we have to apply Fourier transform. So let's say ST is Fourier transform is given as capital S of F. We are interested to see the frequency variations of the modulated signal. Now let us represent the baseband signal in the frequency domain. So let's say MT is the signal representation in the time domain, then its equivalent frequency Fourier transform representation, let's say it is given as MF. So as since MT is a baseband signal or a low frequency signal, that is why we represent in frequency domain, let the maximum frequency be FM, which is the cutoff frequency of the low pass signal, and similarly for the negative frequency in the negative side we can write minus FM, unless its amplitude is M0. Now, the one important question to ask here is, what is the concept of negative frequency? Do the negative frequency, or you can say, whenever we represent any baseband signal in the frequency domain, or any mixture of signal in the frequency domain, we also take into consideration the negative frequencies. But the question is, does negative frequencies exist? So the answer is, when we are dealing with real signals, for example, let's say cos omega ct, let's say a signal x is equal to AC cos omega ct. Now this is a real signal. Now in order to use the concept of complex exponentials, suppose if you represent the cosine signal in Euler notation, it will be given as e to the power j omega ct plus e to the power minus j omega ct upon 2. Now if you look at here, if we represent as a cosine signal, there is no negative frequency, only the positive frequency is available. But in Euler notation, what we find? We find both positive frequencies as well as negative frequencies. And what we are doing? We are taking the average value of both negative and the positive frequencies when we are trying to represent a real signal. Then here comes the concept of negative frequencies. So when we are representing real signals in as a Fourier series sum, or in terms of Fourier transform, then we deal with the concept of complex exponentials. And there are need to consider negative frequency as well. That is why while representing the baseband signal in a frequency domain, we also symmetrically take the value of the signal in the left half of the frequency domain, that is in the negative, we take the negative frequencies as well. But what is the bandwidth of the signal, this message signal? Its bandwidth will be FM only. We are not considering 2 times of FM, because the nature of the signal on the right hand side is the same as the nature of the signal on the left hand side. And one thing more, while we are doing the differentiation between a baseband signal and a passband signal, so a baseband signal is centered around near zero frequency. But when we talk about band pass signal, suppose we are representing a band pass signal, so as you can see, the low pass signal or the baseband signal is centered around the zero frequency. All the frequencies are available near the zero frequency. But in case of band pass signal, If the signal is of band pass nature, then the frequency is centered around some another frequency. Let's say Fc is the center frequency of this band pass signal. Central frequency. In that case, suppose Fm, Fc plus Fm and Fc minus Fm are the corner frequencies of this band pass signal. Let's say this is XF band pass. In that case, the bandwidth of this band pass signal will be given as 2 times of Fm, because the total distance between the two corner points is given by 2 times of Fm. So you can see, in case of the baseband signal, the bandwidth is given by Fm, and in case of the band pass signal it is 2 times of Fm. Now let us quickly move on to representing the modulated wave on the frequency domain. So once again write Sc equals to Ac times of cos 2 pi Fct plus and let's say MT has a Fourier transform MFF, then and we know that using the concept of Fourier transform, if it is multiplied by a complex exponential, then correspondingly in the frequency domain there will be a shift in frequency, which will be given as F minus plus Fc. If MT is multiplied with positive complex exponential, then the change will be right side, and hence and vice versa for negative frequencies it will shift leftward. And if you look at here, if MT is multiplied by cos 2 pi Fc into t, then this can be written as MT times of e to the power j 2 pi Fct plus e to the power j minus 2 pi Fct upon 2. But we will observe in the frequency domain, MT multiplied by complex exponential, then the corresponding capital M will get shifted by an amount Fc. So it will be given by half m f minus fc plus m f plus fc. Similarly, there is another quantity here, cos 2 pi fct. In the now it is given as its equivalent frequency transform will be given as half del f plus fc plus del f minus fc. And finally, we can represent the modulated wave in frequency domain as now st is given as AC cos 2 pi fct plus Ka times of AC into mt cos 2 pi fct. In frequency domain, using the concept of Fourier transform, we can represent SF equal to AC times of AC by 2 del F plus FC del F minus FC. And using this quantity, we can write thus Ka times of AC by 2 F plus Fc plus F minus Fc. So writing this, the same representation graphically, so graphically, if you want to represent in frequency domain, so there is a delta function at the point Fc, at the point minus Fc, at the point Fc, and here you can see the baseband signal is shifted to point minus Fc and plus Fc, and whose amplitude is given as Ka times of AC by 2 and here AC by 2. So first let us represent the delta functions here. Let's say this point is plus Fc and this point is minus Fc, and so this is the delta function and its magnitude is AC by 2. write here AC by 2, AC by 2. And what we see here, the baseband signal is shifted at points FC and minus FC. So as we know, so this is the nature of the baseband signal in frequency domain. So and these points will be FC plus Fn. So because the maximum value of the message signal is maximum frequency of the message signals Fn will be FC minus Fn. Similarly here, symmetrically we can write minus FC plus Fn and minus FC minus Fn. Let's say this is the point 0. And the amplitude is given by Ka into AC by 2. Now, FC is our corner frequency. If we say, or better, FC is called the central frequency. Why? Because the message signal, this is our message signal. Now this message signal is present around this central frequency FC. And this portion of this portion, the portion of the message signal right to the carrier, the central frequency FC, is known as upper sideband. Similarly here, upper sideband. And this portion as well as this portion is called lower sideband. So overall we can say that this modulated wave, it has got three components, three types of frequency components. One is the carrier frequency component, which is given by, which is the FC, the component FC, and the lower side band, and third is the upper side band. Suppose now we are interested to transmit this signal over the radio. Suppose if we write in terms of block diagram, so this is our message signal, this is the carrier wave, and we have done modulation to obtain ST. Now we are interested to transfer this ST over the antenna or radio. Want to do radio transmission. Now see here, the whole message signal is contained in this portion from FC minus FM to FC plus FM. So then what will be the transmission bandwidth? That will be 2 times of FM only. We see the bandwidth, it is given as FC minus FM minus, FC plus FM and FC minus FM. Two times of the maximum frequency of the message signal. And this is the transmission bandwidth. Says Newton Hertz. So what we will do after we have done the modulation, we will apply a band pass filter here. See? Let us apply a band pass filter here. A band pass filter. Centered around the central frequency FC and whose transmission bandwidth is given by 2 times of FM. And finally, we can transfer this, or we can say ST band pass over the radio. So this is the concept of amplitude modulation. Now let's say mt is given as am times of cos 2 pi fmt. Now let's say mt contains only one frequency, which is given by fm. Now we are interested in transferring this signal using the amplitude modulation. Let's say Ct is given as same AC into cos 2 pi Fc into T. Now for this signal, let us write the modulated wave as AC into 1 plus or AC plus MT cos 2 pi FCT. Here again, the amplitude is varying with respect to the message signal. Now AC, let's write as AM cos 2 pi FMT multiplied by cos 2 pi FCT, taking AC outside, 1 plus AM upon AC cos 2 pi FMT cos 2 pi FCT. Now this ratio mu equals to AM upon AC is called modulation index, and since the message signal contains only one frequency FM, then this type of modulation is called single tone modulation. And of course, for satisfactory modulation and to avoid over modulation, the value of modulation index must be less than or equal to 1. Modulation to avoid envelope distortion. And suppose mu goes greater than 1, then this will be the case of over modulation. This is undesired in many cases. So finally we can write ST in case of singleton modulation as AC 1 plus mu times of cos 2 pi FCT into cos 2 pi, this will be FM FC into T. Once again let us represent the same in the in frequency domain spectrum. So st, we write st times of cos 2 pi fct plus mu times of ac into cos 2 pi fm t multiplied by cos 2 pi fct. We can write here as ac times of cos 2 pi fct plus mu times of ac by 2 and cos 2 pi f plus fm t plus cos 2 pi fc minus fm into t. We can observe here for this signal st, how many frequencies are present here? One is fc, one is fc plus fm and fc minus fm. So three types of frequency components are present here. So we can plot the same over the frequency spectrum. So first represent this component, the fc component, which will be given as using a delta function at this point, and symmetrically we will have a negative frequency also. It will be present at the point plus fc and minus fc. And its amplitude will be AC by 2. We have done that earlier. Similarly, we have another frequency component at the point fc plus fm and fc minus fm. And its amplitude will be mu times of AC upon 4 once we represent the cosine function in terms of exponential in terms of complex exponential form or the Euler's form, we'll get an amplitude u times of AC by 4. So this is the representation of the modulated wave for a single tone modulation. We can write it as a single tone modulation. So what are the frequency components available here? frequency components are available here are plus minus Fc, plus Fc minus Fc, and plus minus Fc plus Fm. Similarly, so total 6 frequency components are present. 6 frequency components. Now, let us calculate the transmission efficiency of the amplitude modulation. Or you can say let us consider the case of singleton modulation only. So, again consider this equation. We can write St equals to EC cos 2 pi FCT plus mu times of EC by 2 cos 2 pi FC plus FM into T plus mu times of AC by 2 cos 2 pi Fc minus Fm into T. Now, if we consider this component of St as well as this component of Ft, now this component as well as this component contains the message signal, or you can say this is the signal of our interest, because this is the signal only we want to transfer from one point to another with the help of modulation. So this is the power or that we want to transfer, right? So if this is our central frequency Fc, and let's say this is the lower side band and this is the upper side band, as we have discussed earlier. Also, we know that the average power is given by the square of the RMS value of the sine wave. We have discussed this in the signal system topic. The average power is given by the RMS value, square of the RMS value of the sinusoid signal. So then we can write for this signal let's say the upper sideband power will be given as the RMS value, square of the RMS value. The average power of the upper sideband will be given as mu square AC square upon 8, because the RMS value will be A upon root 2 for a signal A sin omega t. Then in this case, where the value of A is mu times of AC by 2, let us take the unit in watts. Similarly, for the lower side band, it will be same as the upper side band because of the nature of symmetry. And similarly, the carrier power PC, carrier power will be given as AC square upon 2. Then the total power that is being transmitted if given as the carrier power, the upper side band power plus the lower side band power. Now let's say total transmitted power is PT equals to PC times of yes. Then the total transmitted power will be given as PC is given as AC square by 2, and upper side band power is given as mu square into AC square upon 8 plus mu square into AC square upon 8. Now total transmitted power PT will be given as AC square upon 2. Now these are same quantities, that will be 1 plus mu square upon 2 so this is the equation of the transmitted power, total transmitted power. And what is the average value of the message power or the power of the signal of our interest? This will be given by a square by C square by 8 plus, which is nothing but the total power of the upper side band and the lower side band of the message signal. This is mu square AC square by 4, decided in watts. Then the efficiency, transmission efficiency, will be given by theta equals to the average power contained in the message signal upon the total power. The percentage efficiency. So it will be given as eta equals to mu square is square upon 4 divided by AC square by 2 1 plus mu square upon 2, which is given as, if we cancel out these terms, it will be mu square upon 2 plus mu square. You can see the efficiency is given as mu square upon eta depends on modulation index. And we are deriving this equations for modulation index. So once again writing, and for taking, so the maximum value that we can take is 1. So if we put mu is equal to 1, then eta will be equal to 1 by 2 plus 1 is equal to 1 by 3, which will be 33%. Such efficiency we can see is very less efficiency. Very less efficiency. So we can say that the amplitude modulation is not a very efficient method, because the transmission efficiency is coming for the maximum value of modulation index is only 33%. Now once again writing total transmitted power as Et equals to AC square by 2 1 plus mu square by 2. Now it can also be written as PT into PC. C is the carrier power, AC square by 2 is the carrier power, 1 plus mu square by 2. Now suppose this modulated signal we want to transfer over the antenna. Then let's say IT as the transmission current, and IC be the carrier current. Because before the wireless transfer, the modulated signal is being passed through electrically, and let's say R be the antenna resistance. In that case, Pt will be given as, and similarly now normalizing this equation, we can write IT square equals to normalizing with R. So we can write this ratio as the conduction ratio of conduction current, the transmission current upon the carrier current will be given as under root 1 plus mu square by 2. Now this is the case of single tone modulation. Suppose the message signal MT contains multiple frequencies, say AM1 cos 2 pi FM1 into T plus AM2 cos 2 pi FM2 into T and so on. Let's say AM, and it contains n number of frequencies. So in that case, if we want to represent the modulated wave, then let's say if we write AC times of 1 plus mu1 cos 2 pi FM1 T mu2 cos 2 pi FM2 T and so on up to n times. T into cos 2 pi FCT. So in this case, the total modulation, let's say if mu t, can be written as the sum of the square of the individual modulation indices. And in that case, the total transfer power will be written as 1 plus mu1 square by 2 plus mu2 square by 2 plus mu3 square by 2 up to n times. Or we can write overall we can write on this will be the case of multi-tone modulation. And similarly, in terms of current, you can write the ratio of the transmitted current upon the carrier current 1 plus so thank you.